All right, so in the previous lesson we saw, okay, how do we kind of use multiple neurons in a single layer, right? Remember we had those two separate neurons. And we said maybe one neuron is determining the cell's size and the other neuron is something about the cell's shape. And these outputs are then going to be fed forward to the next layer. And maybe we'll combine these outputs to make another determination. And feeding those outputs to the next layer, well, that's the topic of this lesson. All right, so, this is what we saw in the last lesson, right? Remember, we had this single observation, had 4 features, and here this diagram is showing actually 4 separate neurons, each of which is applying a linear function wrapped in our activation function, right? Our sigmoid function. And to show this in matrix algebra, right, this linear layer with multiple neurons, it looks like this, right? Where you have that single vector with multiple features that's applied now to a weight matrix, all right? And then finally we add the bias term. So right here is our feature vector, right? And maybe it has, something about those 2 features about the size and those 2 features about the shape. And then we multiply this vector first by our first neuron's weights and then by our second neuron's weights. And that gives us, right, that means that we're basically doing the dot product to this first neuron, this second neuron, and that's giving us a number, right? X dotted with W1, that weight vector, comma, X dotted with W2, that weight vector. In my mind, this is giving back a number here and a number there, right? Like -5 and 7. And then to these 2 numbers, we add our biases, right? So we have W plus B, right? This is the first neuron's weights and bias. This is the second neuron's weights and bias. And then so finally, performing those operations, we then get the output from the linear layer. And this will give us maybe a number, -2 and a number +3. And then to each of these 2 entries, we apply the sigmoid function. Cool. So that is, feeding through data to these separate neurons. Each neuron is then going to give an output of like 0 to 1. And we can think of them as assessing different things, like this one's assessing the size, this one's assessing the shape, right? If we had more, maybe this one assesses the color, right? How maybe this one's just assessing contrast. I don't know. Okay, so this is multiple neurons, but to then think about how do we now take these outputs. This guy's told me that this is a large neuron, and this guy's told me that this is, an irregularly shaped neuron, and this one's told me that it's a light neuron. But we want to maybe combine these inputs to now make the next determination, okay? Like maybe this one's in charge of telling me, is this a light and large neuron, which maybe means something. Or sorry, not neuron, but cell, a light and large cell. So to do this, to think about like passing through the data from one layer to the next, we will have to talk about, this just involves some math, okay? And it's not so bad, but we do have to say the word. So we'll have to go through a couple of rules about matrix multiplication. So let's see this. This is exactly what we saw before, right? So we're going to start with our weight vector, and this is the weight matrix. And this weight matrix has the weights for our first neuron and our second neuron, right? So remember, this might be, we can kind of think of this matrix as 2 separate vectors, 2 separate weight vectors, one for 2 neurons in a layer, okay? And as we saw, maybe this guy seems to be emphasizing the first 2 features. This one seems to be emphasizing the last 2 features. So this one maybe is more influenced by changes in size, and this one more by changes in shape. And then as we know, right, this is my actual feature vector. And yeah, we can start by calculating the weighted sum. So how do we do that? Well, we just do the dot product, apply the dot product to each of these vectors separately. And what will the output be? Maybe we can guess. If we apply the dot product to this guy and to this guy, right, we should get a vector of length 2. Let's see that. So if I do x1, that's representing my first observation, at w, that's this guy right here. Well, this is two neurons. Each neuron is both going to have an output by applying the dot product. So you can see that this is of length 2. We can really see that if we do dot shape. All right, so this is saying 1 row by 2 columns, but we'll get into that later. All right, so that's what I'm saying, focus on the dimensions. Okay, so I guess we'll get into it now. So what I mean is we started with a weight matrix. Okay, we started with a weight matrix like this. And if you call shape, this tells you the number of rows and the number of columns. So we have 2 columns, 1 for each neuron, and each of those neurons has 4 rows. Okay, so this is we'd say this is a 4 by 2 matrix. In linear algebra, in PyTorch, you always specify the rows first. Okay, so it's 4 by 2. Now let's look at x. So I wrote x1 a little differently than previously. When I created it, you may notice this. What I did was I actually wrapped it in 2 things. So this is like an outer list, I guess. And the reason I did this is because I want to make sure, I want to kind of specify, hey, we can think of this vector as really a matrix with a single row in it. Okay? So let's just confirm that this is a single row and not a single column, and we can, right? How do we know that? Well, remember, the rows always come first. So this is saying 1 row by 4 columns. Okay? Whereas this was 4 rows by 2 columns. Okay, 4 rows by 2 columns, 1 row by 4 columns. Believe it or not, these dimensions are important to understanding, neural networks. Okay, so why is this important? The reason why, so we had, if we think about what we did, we had a 1 by 4 matrix. It's a vector, but really, technically, it's also a matrix. And so it's a matrix with 1 row in it. This guy. Okay. And we're going to multiply it by a 4 by 2. All right. If you just look at the dimensions, you can determine the output. You can kind of figure out the dimensions of the output, meaning that if you just look at the dimensions and you do x1 at w, you can look at these dimensions and say, oh yeah, this is going to be a 1 by 2 matrix. Let's take a look at that. See that? 1 row, 2 columns. Let's take a look. That's exactly what it is. 1 row, 2 columns. Okay? So how do we do that? The outer dimensions are when we do matrix multiplication, we are multiplying here, in this example, a 1 by 4 matrix by a 4 by 2 matrix. And the outer dimensions determine the shape of the product. Okay? So this is 1 by 4 by 4 by 2. What are the outer dimensions? Well, this is on the left. This is on the right. So let's just make this even more clear. If you think of this, this is an x sub 1 by 4, and we're multiplying that with a w, which is a 4 by 2. All right? I'll just use the dot product for now. Okay, so we're multiplying these together. The outer dimensions, 1, 2, right? These are the outer dimensions, is going to determine the shape of the product. Right? 1, 2. The inner dimensions, I must have said this wrong. This is 1 by 4, I'm so sorry. The inner dimensions must be equal for our matrix multiplication to work. Now this should actually make sense to you, because if you think about what happens here, we are multiplying here we are doing the dot product, right? We are saying, okay, we're going to multiply the entries of this by the entries of this column, right? So we're kind of lining up this one row, 4 columns, 4 columns with these for the entries in of this column. So this has to equal this. If it doesn't, if we only had 3 and we're multiplying by something that's 4, that's not how we understand the dot product. Okay? So the outer dimensions are telling us what the product's dimensions are going to be, right? What this will result in a vector with 2 entries in it. And the inner one is saying, yes, this compiles. Because if these two are not equal, then we simply cannot perform matrix multiplication. Let me show you that. So here, let's say I added an extra feature, okay? And now I try to do x1. Let's look at x1.shape. x1.shape. This time it's 1 by 5, 1 row, 5 columns. And now let's look at w.shape, 4 by 2. So if we want to say, does this compile, the first thing we do is we kind of, stack these together, and we say, all right, this is 1 by 5, and this is a 4 by 2, and we take a look at the inner dimensions, and we say these are not equal, and this will not work. Let's try it. So now we're going to do x sub 1 at, because that's how we do matrix multiplication, w. And let's see the answer. Matrix 1 and matrix 2 shapes cannot be multiplied. Look at what PyTorch is telling us. 1 by 5 and 4 by 2, silly, right? 5 and 4 do not equal each other. So that's exactly the error it's giving us. So the reason why we need to know this is because when we're passing, when we're stacking layers, we're going to pass outputs from one layer to be the inputs of the next layer. We'll see this in a little bit. But for right now, let's just make sure we kind of hold on to these rules of matrix multiplication. What we saw so far, right, is like these 2 rules. 1, the inner dimensions must be equal. And 2, the outer dimensions determine the dimensions of the resulting matrix. Let's say in matrix multiplication, right? The inner dimensions must be equal. The outer dimensions determine the dimensions of the resulting matrix. Let's just see this one more time. Let's start with our x1. This is a 1 by 5. Let's just copy this. This is torch.tensor. That's going to be our, let's call this x2. All right. And then let's get our weight. So that's this thing. Now, if we think about this, now we have our weights. Again, close down Slack. So if we have our weights, w.shape, this is a 4 by 2 right now. How do we fix that? Let's look at the w. Well, we need to have each of these vectors be of length 5. So let's just add another number. 3, let's say negative 4. Okay, now let's look at the dimensions. W.shape, 5 by 2. Now we are about to do this. We're about to do x multiplied by w. But before we do that, let's confirm that the dimensions are good. So how do we do that? We do x.shape, comma, w.shape. And it breaks because I want x2.shape. So what does this tell us? Well, the first thing my eyes are doing is going towards the inner dimensions. So here 5 is 5. 5 and 5 are the same number. Good thing I'm teaching you guys. So we have 5 and 5 are the same number. And now the next thing maybe you're guessing is, okay, well, what is the resulting matrix, right? So far so good. It looks like we are stacking this thing of length 5 and dotting it with this guy of length 5, and we're doing that again here. So just like logically, it seems like we will be getting an output of a single a single vector that's of length 2, right? Because we have 2 separate neurons here. And also using our rules, x2 with w, we see that exact same thing, right? We see 1 row and 2 columns. How do I know this is a row and not a column? The only way I can do it is just by calling the shape and confirming. All right, 1 row, 2 columns, which is exactly what our rule tells us. Okay? So why this matters? This matters because, what we're going to have to do is we're going to have to specify, well, how many neurons and how many weights we want in each of those neurons when we build our neural network. And to do that, we need to have some intuition about how I can, how many neurons to put in a layer and how long these neurons can be. Because it seems like if I don't specify the correct dimensions here, well, then my neural network will break because there's going to be a mismatch between the data, in my matrix multiplication. So we'll see that a little bit better. Let's think about this. What this is representing is an observation with 6 features in it. So we're saying, okay, maybe with my potentially cancerous cells, now we have 6 features. And then what is this saying? This is saying that we have 4 separate neurons, right? Each making a separate determination. And the light and dark, what I'm just doing is I'm saying, remember the light bulb analogy? I'm essentially saying, well, this is how much they are, lighting up. Each neuron is lighting up or not lighting up. This guy's talking about the size, and it seems like it's not too large, so it's not lighting up. This guy's talking about the shape, seems like it's pretty irregular, so it is lighting up, and so on. Then these numbers, these 4, so we, pass this data in, we're going to get an output, right, from that sigmoid layer, from each one of these neurons. These neurons are now, these outputs are now going to be passed forward to each of these neurons. So this next layer is getting 4 values from the previous layer's neurons. You can see that, right? This is going here, this is going here, this is going here, this is going here. So this neuron maybe is in charge of, detecting cancer cells that are large and weirdly shaped. And this neuron maybe is in charge of detecting cancer cells that are small and weirdly shaped, right? So they can kind of take the inputs from the previous layer to now make their own determination, right? And mathematically what that means is we need to, all they're doing is they're just kind of taking these values and multiplying these values by a set of weights and a bias term to produce an output again. So let's see that, all right? Let's see. It might feel confusing, but let's just hang on and see that. So this is the first observation, and the key thing here is just focusing on the dimensions. So we have 6 features and 4 neurons. So what does that mean? We have a vector, 6 features. 1 row, a single observation, 6 features. What's next? Well, we want, how many neurons do we want? 4. So that means we want, let's think about this. We also need to have each of these neurons taking in these 6 features. So that means we want to have 6 rows, right? Each and 4 separate neurons, 4 separate columns. So this should be a 6x4, I think, right? 6 rows, 1, 2, 3, 4, 5, 6, 4 separate columns, 1 for each of these neurons. So now you look at this shape and you kind of say, okay, here's this x2, I suppose. Let's make sure I actually ran this. x2 dot shape, and we're going to multiply it with w1 to now produce a prediction or output from the linear layer for each neuron. Okay, or at least get there, we need to do this dot product. So okay, so how do we do that? Well, we do x2 at w1, right? This first weight matrix, and that produces. It should produce. First of all, should compile because these are aligning. Should produce 1 row for length 4, and that's what we see. Okay, and then we also now, this is just the dot product of each of our neurons. We still need to add in the bias term. So this is the bias of that first layer, right? This is the bias of the first neuron and second and third and fourth. So the whole thing is really x2 plus b sub 1. And that's the output from the linear layer. So we can think of this as this part before we have applied the sigmoid function. Now let's apply the sigmoid function. All we have to do is do torch.sigmoid, I think, to this linear layer z. And there we go. This is a huge number, so it's giving us something effectively 1. This is a larger negative number, so it's saying, okay, we're not, whatever this neuron's in charge of, maybe it's in charge of determining color, and it's saying it's not very red, or whatever color it's looking for. Okay, so now we want to take these outputs and pass them now to the second layer. Let's go back to our diagram again. So these are the outputs we just saw. Let's pretend. And now we want to pass these outputs to the second layer. Okay, so how does that work? Well, if you think about it, the outputs we just saw, A2, is a vector. And we kind of know how to do that. We can, we produce like so this is the outputs we just saw, and we want to pass this to our second layer, and this is the second layer, and this is here maybe why this makes sense is if you remember, there were 3 separate neurons, right? And how long does each neuron need to be? Well, each neuron needs to take in the outputs from the previous layer. So we had 4 outputs from layer 1, 1 for each of the neurons. Right? Each neuron gave us back an output. And now I'm going to pass those 4 outputs from the previous layer to each of these neurons. So what does that tell us? It means that we need each vector, each neuron, to have a vector of length 4. You see that? 1, 2, 3, 4. 1, 2, 3, 4. And here we're having 3 neurons. So let's use our rules again. So what we are about to do is say, okay, let's take this vector and multiply it by W2. That's essentially what we did before, right? Before with the earlier layer, we said, let's take, x sub 1 and multiply it by W1. That gave us, and then we applied the sigmoid function. And we added this b. And now that we got that, this gave us something that is 1 row and I think a 1 by 4. It might be a 4 by 1. It is a 1 by 4. Okay, and now we want to take this and multiply this by our second thing. So this is just another vector that now we're multiplying by a second weight matrix. Okay, and we can kind of play the same game and say, will it compile, right? And how do we know that? Well, we look at the shapes, and we say A1.shape, and we say W2.shape, and we look at our rules again and say, well, the inner dimensions better be equal, and they are, which makes sense. We are taking this, output from our 4 neurons and then dotting it with each of these vectors. So they are the same shape. And then we say to predict the output, what am I going to get back? Well, I'm getting back, an output from each neuron, right? So this is 1 by 3. We had 3 neurons. Each one is producing a separate dot product. So that should give us 1 to 4, apply it, dot it with this matrix, right? And then that should give us back a vector, 1 of length 3, 1 output for each of our separate neurons. But that's only part of the linear layer. The next thing is to add B2. And then we're done, right? This is now, if you do this, B2 is not defined. B2, here it is. Right? Now we get the output from our second layer. Our second linear layer, I should say. What's next? We apply the sigmoid function. So this is our Z2. And then what do we do next? You just apply the sigmoid function. Torch.sigmoid applied to this is going to reduce these values down to a number between 0 and 1. Okay? So you can kind of see how we are using our knowledge of like matrix algebra to specify or figure out and perform this multiplication. There are 6 entries here, right? So this is a 1 row. Let's just summarize. This is a 1 row by 6. That's like my x1. Okay. Then I'm going to do matrix multiplication. Do x1 times by w1. What's w1? Well, we know that it has to take each. There must be 6 rows to it, and there's 4 neurons. So this is a 6 by 4. And then we can kind of use our knowledge of matrix algebra to confirm what we saw intuitively. And that's that, okay, these line up in each of our neurons, so it will compile, and each of our neurons is producing a separate output. So that's going to give us a 1 by 4. Separate this out. That will give us back a 1 by 4. Then we go to the next layer. The next layer, here we get these 4 outputs. So that means W2, we're about to do, this is like my A1, if I apply my sigmoid to this, right? And now we're about to do W2. Well, that's going to take in the A1, which you can think of as just a 1 by 4 vector. And now we're going to do that, I should do lowercase because it's a vector, with W2. And what should W2 be? Well, if this was a 1 by 4, that means that W2 has to have dimensions of 4 rows, because the inner dimensions must be equal, right? And we're basically going to take these outputs and dot it with each of these vectors, and that we want 3 neurons. And then from there, if we do a 1 by 4 with a 4 by 3, what do we get? We get a 1 by 3 output. So this results in 1 by 3. Okay? So that's pretty good. And then we apply the sigmoid, but that keeps the same dimensions. We have to add b. And apply the sigmoid. And we have to do that here, but that also just keeps the same dimensions. All right. So that's kind of the point, is that we can develop intuition. The other thing you can see, and maybe I should specify, is the length, the size of each neuron's vectors. That's determined by the previous input, by the previous layer. But how many neurons we used, that's up for grabs. And there are different, neural network architects that kind of make those dimensions, make those decisions, and there are rules of thumb there. But for instance, if the reason why this is important is because even in PyTorch, if you think about how we're going to have to build this thing, we're going to have to do something like nn.linear and specify, how many neurons. But really, what we care about is how many the inputs, that it's going to be able to take. So if we have a data set where each observation has 6 features, then this better say 6 first. And then we have, this is saying that we have 4 neurons. And then comma, we pass that to our sigmoid function. And then we do the next thing. And now we kind of think about, well, what does this next linear layer need to take in? Well, there's 4 neurons, right, that are each producing an output. And that means this guy better take in a vector of length 4, right? Because all those outputs, right, this is like one combined vector of outputs that are now being passed here. And now how many neurons do you want? Well, again, it's up to you. Like maybe you say 3, okay? Now the thing we have to see next, and we will see this next, is what do we do with that last layer, all right? Because we just have to talk about that. That's kind of a special layer. So that's what we'll talk about next. But all these rules of matrix algebra, they're all in this section, so I encourage you to take a look at it if you feel like you need a little bit more help. All right, see you guys later.